Good morning, good afternoon, and good evening, everyone. So today we're going to be doing some exercises on velocity, speed, acceleration. So basically the previous calculus video we talked about. Um, so just a brief review. So in our last video in the calculus series, well, we talked about velocity, speed, and acceleration in terms of vectors. And so we just went through that and we were able to use some formulas, but really it's just calculus since we have our position vector. We take its derivative to get our velocity vector, and we take its derivative again to get the acceleration vector. And if we want to switch back to our velocity and our position vector, then we just integrate. So we talked about that, and we also talked about projectile motion. Um, it's this idea of having a projectile fire, right? Fire at some point, and it's going to land at another point in our xy coordinate plane. Yes, we were able to do parametric equations. We were able to derive parametric equations. We also did a couple of exercises on projectile motion, but it's really all about just deriving velocity, speed, and acceleration, and finding that projectile motion, finding the formulas needed to track the projectile. And lastly, we talked about tangential and normal components of acceleration. So here we were able to look at acceleration more deeply through its two components. And we were able to find formulas for both of these just in terms of r, or in terms of our position vector and its derivatives. And yeah, that's pretty much it. So we're just going to be diving into some exercises here. So let's do it. So for number one, um, here we want to find the velocity, acceleration, and speed. Okay. So we want to find velocity, acceleration, and speed of a particle with a given position function. So let's just fully write that out. And our position function, position vector function, let's just do position function because you already know it's a vector. Let's say it's r of t with components. Oh, it's written in ij. I'll write it in vector form. So 7 um, cosine of t, comma, what's this? 6 sine of t. Great. So first, let's find, or actually, we can find all of these in one go. But let's find velocity. So velocity is just the derivative of our position vector function. So I'm saying my velocity function or my velocity vector function is just the derivative of my position function. And so this is 7, negative 7 sine t, 6 cosine t, and that's it. Done. Acceleration is basically, from what we previously discussed, it's the derivative of my velocity vector. So my acceleration is the derivative of my velocity vector, which we can also say is the second derivative of my position vector. And so we basically just take the derivative of these components. So this is negative 7 cosine t for my x component. And for my y component, it's negative 6 sine t. Right? What else? We're also being asked to find the speed. And if we remembered from a previous discussion, well, speed is just the magnitude of my velocity. So the magnitude of this is my speed. And so I'm just going to use a distance formula. And I plug in my components, my x and y components of my velocity vector. And I solve accordingly. Or I simplify, actually. So let me just simplify. Here I get 49 sine squared t. I added to 36 cosine squared t. And we're done. Okay, let me just type all of that in before we're good to go. So again, my velocity vector has components x, which is negative sine t, comma 6 cosine t, and close that vector. For my acceleration vector, it's the derivative of my velocity vector. So it's negative 7 cosine t, comma, oh, why did I say cosine? I meant sine. Oh, wait, what? What is a, oh, negative 7 cosine t, yeah. Apparently, yeah, I'm confused. I forgot the, this is why I boxed my final answers. Because then I'm looking at the wrong thing. Negative 7 cosine t, comma, negative 6 sine t. And we're done. And lastly, for my velocity or my speed, it's just the distance of my velocity vector. So it's the square root, I like the square root here, square root of 49 sine squared. I do that, but sine squared t, and I add it. I add it to 36 cosine, put the square here. Done. He forgot that. I hope he did. Nice, got it. Okay, now we're being asked to sketch the path of the particle. And draw the velocity and acceleration vectors. So, and draw our velocity and acceleration vectors. In particular, for t equals pi third over 3. So how do we do this? Well, let's plug in everything first. So for R of t, for V of t, for A of t. So that's first thing I would do is plug in. So that we know what we're looking for. So if I plug in pi over 3 for my position vector, I get 7 cosine pi third pi over 3, comma, and then I get 6 sine pi over 3. So here I'm just substituting pi over 3 for t, for my parameter t. Now, I'm going to be honest, I don't know what that is. So I'm going to look at the trigonometry table. This is what you get for not memorizing. So for cosine pi third, it's actually 1/2. This is 1/2. This is 7 over 2. So 7 times 1/2. And then okay, let me have my trig table here. And then we have square root of 3 over 2 for this one. And so I just divide 6 by 2, I get 3 square root of 3. So it's cleaner. Okay, and then next we take our v, our velocity vector. We plug in pi over 3. And we do the same thing. Instead of t, we're going to substitute pi over 3 with it. So we have negative 7 sine pi over 3. And what was the other one? 6 cosine pi over 3. Okay. So again, cosine pi third was 1/2. Let's just put 1/2 here, just so that I know what values I'm looking for. Then here we said this was square root of 3 over 2. Okay. So this is going to be negative 7 and then sine. So yeah, this is going to be negative 7 square root of 3 over 2. And then my y component is going to be 3. 6 divided by 2 is 3. And lastly, let's put a, my acceleration. So this is going to be what? I don't know. We plug it in and we'll find out. Negative 7 cosine. So actually this is the same as my position vector for some reason. But the difference is that it's negative. That's the only difference. So this is just going to be negative. Okay. Now from here, what do we do? Well, that certainly helped. Now we're going to sketch, right? So we sketch the path of the particle and we draw V of t, A of t. Okay, so let's quickly do that. So here we sketch. We're going to start with our position vector. So this is my xy plane. So where's our what's this? Where's our r pointing towards? It's pointing 7/2. So what's that in decimal? I'm just gonna approximate. Like 3.5 to the right, maybe? Somewhere here. 3.5 to the right. And 3 square root of 3 up. So what is that? So like 5.1-ish, 5.2-ish. So my r of t is probably pointing somewhere here at pi third. Which makes sense, right? Now this makes a pi third. Yeah. I just realized that. Yeah. See, here's the thing. I'm not good at angles. Okay, so I just realized that was pi third. Okay. And then what happened here? Well, we say, okay, our velocity vector, we go down negative 7 square root of 3 over 2. Now we go to the left, actually. Left x times, and then up by 3. So what does that look like? Okay, here I'm going to give a rough estimate, but I would say it kind of looks like this. So that's my V of t. And then this is my R of t. Okay, what else? So I kind of go to the left, right? X times. And then I go up 3 times. So just imagine that's how it looks like. Not drawn to scale, by the way. And then lastly, we have our acceleration. So our acceleration actually also starts from my point, from where I'm at. So I go negative. Okay, so I go here, left, and then I go down. I think that's how it's supposed to be, right? I hope that's how it's supposed to be. If not, I'm gonna recheck my. But basically, it's just this thing again. Oh crap! Because I'm going at the same vector, but I'm just switching its direction, right? So it should be the same length as my position vector. So I think it's that. But again, I'm not super confident. So especially when I haven't seen it before. But yeah, let me actually double check to see if I'm doing it. Okay, it kind of goes there and goes down. Okay, this is the same number. Oh, it's a different number, but oh well, it should be the same approach. Okay, that should be it. Nice, got it. Okay, we move on to number two. So for number two, we're being asked to again find velocity. So it's actually the same thing. We're asked to find velocity, speed, and acceleration. And here um we're given a vector, a position function. So we're given r of t, which is I'm gonna translate that immediately to vector form. So it has components t, t squared, and because it's an ijk and 5. Right. So here I find everything I need. So I find velocity by taking its derivative. So I get 1, 2t, 0. Then I find my acceleration. So here I get my acceleration. So I just take the derivative of my velocity vector. I get 0, I get 2, I get 0. And then I find my speed. So here I get the magnitude of my velocity. So I do a distance formula. So really, honestly, what math is in academia, in my opinion, well, at least from my experience studying, it's usually about finding patterns, less on the application part, unfortunately. So the idea is you do the homework, you memorize the pattern. That's why I always make notes of what the pattern is. And then I just put them in my note sheet during a test or an exam. So yeah, it's those stuff. Anyways, so now we've found our velocity, acceleration, and speed, right? Let me just type it in. So my velocity is 1, 2, 3, 0. My acceleration is 0 to 0. My magnitude is square root of 1 plus 40 squared. Okay. And okay, let me just see if we got that. I hope we did. And okay, we got it. Now we're being asked to sketch the path of the particle and draw the velocity and acceleration vectors at a specific t. So again, with the sketching, so we're being asked to sketch path of particle and draw my velocity and acceleration at our parameter t equal 1. Okay. Okay, there's like a fill in the blanks here. It says that v of 1 starts at the endpoint of r of 1 at what? So here I'm not going to go through it anymore, but I'm going to do what we did in the previous one, which was I plug in. So I'm going to do that same pattern here. So I plug in, I get r of 1. And instead of t, I put 1. So I have 1, 1, 5, right? And I'm done with that. So that's where it starts. It starts at 1, 1, 5. So my v of 1 starts at the endpoint or at the head, the terminal point, the head or the terminal point of r of 1. That's going to be the tail of my velocity vector. And where does it end? Now that's a good question. So here, I have to find my velocity vector at t equals 1. And then I have to add it to my components here, right? So it's asking where does it end, my velocity vector. It should end at some point. So I'm going to find my v of 1. I need my vector to do that. So what do I have? 1, 2, 0. Okay. 1, 2, 0. So, okay, let me just write that out. So v of 1 starts at what point? Starts at point 1, 1, 5 and ends at what? I basically just add these components. I get 2, 3, 5. Done. I start from that point. I use this vector, and I get this point. So those are my two answers in the first part. So I start at 1, 1, 5, and I end at the order triple 2, 3. All right, 2, 3, 5. Yeah, that's if I didn't make a mistake in my addition. Okay, let me just double check, see if I got that. Okay, got it. And same idea. So a of 1 starts at the endpoint of r of 1. So here this one actually also starts at the same point as v1 starts. V1 starts. But where it ends is different. It ends somewhere differently. So that's where I'm going to use my vector. I need my vector to do that. So my a of 1, oh, it's just 0 to 0. And so here I add everything I need to add. 1 plus 0, I'm adding these. They're the corresponding components. I get 1, 1 plus 2, 3, 5 plus 0, 5. So I end at 1, 3, 5. Here I start at the same point as v of 1 starts. And let me see. Let me just, oh crap. Okay. I think that's it, right? Yeah, that's it. Okay. Next one. Number 3. So again, we're being asked to find the velocity, acceleration, and speed. So I'm going to copy paste. Also, another thing I realized about math is this. We're given repetitive problems. So that we get used to the tools that we're learning. So in this case, we're learning how to take derivatives of vector functions. Pretty much how to take derivatives and integrals. Okay, so here it's a good thing they put it in vector form. I'm happy about that. So my x component, my y component, and my z component, which are all functions in terms of t. Okay, now I find my velocity. So again, same step. Literally the same step. So my VFD is just the derivative of my r. I take the derivative, I get 2t plus 1 for my x. I got 2t minus 1 for my y. And I got, what's this, 21? 21 t squared for my z. Right, because I multiply 7 to 3, and then 3 minus 1 is 2. That's a derivative technique from Calculus 1. What else? That's fine. Now we find acceleration. So here I take the derivative of the previous vector I got. So my velocity vector. Here, this is just 2. This is 2. This is 21 times 2, 42. 42t. So again, I multiply my exponent to my numerical coefficient, and I subtract my exponent by 1. Yeah, 1 times 2, 2, 2. Yeah, okay, okay. See, the thing is, I'm doubting myself when it comes to these arithmetic. Usually, this is where I get my mistakes. Okay, next we find my speed, or the speed of this vector, this position vector. And so we get the magnitude of my velocity. I could even say the magnitude of the derivative of my r, but same thing. And so I get my distance formula. And I put all of this squared. So that's a pretty long formula. But hey, math is math. So I just plug in everything, put them squared. And I think, do I simplify here? Well, if I were to use it, I would. But in this case, I'm not going to do it. Because that was the end of the question. But if it was asking for something like, okay, plug this in, maybe I might simplify it to make it more cleaner. But in this case, I don't want to. But to be honest, it's a good practice to simplify everything. But for the sake of time and efficiency, I'm not going to do it. 2t plus 1. Here I'm just plugging everything. Did I reverse it? Oh, no, I didn't. Yeah, 2t plus 1, 2t minus 1. Okay, cool. And then 21 t squared. Okay, my acceleration is 2242t. 2242. And lastly, my magnitude of my velocity, my speed, is the square root of this thing. The square root of my x component squared. So 2t plus 1, I square that. I add my y component squared, minus 1 squared. And I add my z component squared. So 21t squared squared. And let me see. I hope I got it. Oh, wait. Was that 7? Okay. At first I thought it was a 1. Let's double check. Oh, the answer cannot be understood. Oh, oh crap. My bad. I put the arrow in the exponent. That's funny. Okay, now this should be good. Nice. Okay. And now we'll do one last one, then we'll take a break because I don't want the video to be too long. So here we're being asked in reverse now. We want to find the position vector. I'm gonna put a name for it already. I don't care. The textbook didn't. I like putting names already. Of a particle. What does the textbook say? Maybe I can shorten. Maybe I can shorten what it's saying. So it wants me to find velocity, position vector that has given acceleration and specified initial velocity and position. Then on your own, using a computer, graph the path of the particle. Okay, let's just, okay, so here's what I'm gonna do. Using given, I'm just gonna write the given. But basically what it's saying is my acceleration is given. So this is, I'm immediately converting it to vector. The vector form, 20t sine t cosine 2t. That's scary. Okay. And then my, I have other conditions here. So I have my velocity vector at t equals 0 is, oh, it's I. Oh, so it's, I'm gonna write that like this. That's a standard basis vector. And my position vector at t equals 0 is j. So that's 0, 1, 0. Right. So what do I do? Well, I integrate to get velocity vector. So this is just two long integrations. So I integrate my acceleration function to get the velocity function. I again integrate my velocity function to get my position function. So let's do that. So to get my velocity, I integrate my acceleration function. And so if I integrate, then I have to integrate its corresponding components. Oops, forgot to write ut. Sine t, dt, sine, no, cosine 2t, dt. Cool. Okay, let's do it one by one. See, when it comes to integrating, I really can't do this in one go. So usually I have to take steps to do this. So let's start with the first component. So when I integrate this, I'll take out my constant. Now I'm left with t dt. And then from here, I take the antiderivative of my variable. Then I add a constant. And then I get 10t squared plus that constant. How do I know if I'm correct? Well, I take the derivative. And this gives me 20t plus 0. So that's just 20t. So this means I'm correct. Okay, now we get sine of t. Here we just immediately know what this is. This is negative cosine of t plus some constant c2. How do I know? When I take the derivative of this, I get negative sine plus 0. And so minus minus, that makes it positive. So done. And lastly, cosine 2t. I think this is the most difficult one. So here, I need to use a trig identity. That trig identity is a half angle identity. So that's 1/2. Here, I just memorized this. 1, I think it was 1 plus, I forgot if it was a sine. or a cosine. Oh wait, no, my bad. That was for squared. Oopsies. Scrap everything I said. So here I just do sine. I think I do, yeah, it was 1/2 sine 2t. How do I know? Well, I integrate. But here I just guess. So 1/2, that's done. I integrate this, so I get cosine of 2t, and I take the chain rule, so I get 2. Oh, and then this cancels. Done. So that means I got it. So usually determine if you integrated it correctly, you differentiate it, or you take the derivative. Because they're just inverses. What else? Okay, I just copy the thing. Oh no, I don't need to do that. I can now find constants here. So I'm gonna find the constants. We're gonna use my v of 0 here. So I'm saying that when 10 times 0 squared plus c1. So when my t is 0, my answer should be, for my x component, it should be 1. So here I realize, okay, my c1, my first constant is 1. For my y component, my next component, my y component, negative cosine, I plug in the 0 plus c2. This is equal to what? It's equal to 0. Now I solve for c2. Now cosine 0 is 1, if I'm not mistaken. Yeah. So that means c2 is 1, right? 1, 1. 1 minus 1, 0. And lastly, what else? Oh, there. My 1/2 sine of 2t plus c3 is equal to 0. So if I plug in my 0 here, I get sine of 0, which is 0. So c3 is just 0. So the idea is finding these constants here. And then we have our velocity vector, which is 10t squared plus 1 negative cosine t plus 1. And then 1/2 sine 2t. There we go. Yeah, I'm not trying to simplify it yet because I know I'm going to integrate it again. Okay, done. Now I found that part. So let me just do a little check mark. Okay, now I integrate again. I do the same whole thing again in order to now find my R of t to get position. So previously in the last 3 exercises, we've been taking derivative to find acceleration. Here we're doing it in reverse. We're given the acceleration, now we integrate to find its position. Okay, so my position is the integral of my velocity vector. And so if I take the integral of a vector function, I have to take the integral of its component functions. That's the number 1 rule. No space. However, I'm just gonna go for it. It's okay. I can just scroll. Oops. Okay, and I think that should be good. Great. Now I integrate one by one. So the first component here. Well, this is just what is this? Well, I go straight to integrating it. So I got 10 t cubed over 3 plus t. And I have my constant. Uh, yeah, that's it. I could make it cleaner now. I could say 10 t cubed over 3 plus t. Yeah, I'm fine with that. Plus c. I don't care if, yeah, that's fine. Okay, now my next one is negative cosine t plus 1 dt. So here I integrate it again. Uh, when you integrate cosine, it's just sine. So when you integrate negative cosine, it's negative sine. I'm gonna add it to 1. So that's just t. Okay, that's it. I'm gonna make it clean. I'm gonna say t minus sine t. Yeah, that's it. Then c2. I don't even need this. Just put it. Yeah, that's it. Nice. Little bit of OCD. I'm kidding. Okay, and then our last one is 1/2 sine 2t. So here I can get rid of my 1/2. So usually when you have constants, when you're integrating, at least something I learned from calculus 2 is to get rid of them. You want to not make it too complicated. You want to keep it simple as you can. Okay, we have sine 2t. When we integrate, this is just going to be what? Like, I think it was negative 1/2 cosine 2t. Let's try. We take the derivative. I leave this. This one becomes a negative sine 2t. Then I add a chain rule here. So that's 2. And so if I cancel and I multiply, so I get sine 2t. Okay. And so I get 1/2 times this. Oof, can't see. Plus some constant. And then I can just simplify. I have negative 1/4. There we go. As clean as we can. Great. Done. Now we find the constants. So what's the information that we have? Well, we're given that r of 0 has components 0, 1, 0. That's our vector. So we plug in 0 for each of these components, and we should be able to find our constants. So for my first component, I plug in the 0 over 3 plus, what was this? Plus t. So that's plus 0 plus c1 is equal to what? 0. So my c1 is 0. Okay, well, my second component is t, 0, minus sine of t, so sine of 0, plus c2. So again, this just cancels. Everything's just gone. This is just c2 equals what? C2 equals 1. So that's my answer. C2 is equal to 1. And lastly, we have negative 1/4 sine of, oh, my bad. Negative 1/4 cosine of 2t, so 2 times 0, which is just 1, plus c3 is equal to what? I'm assuming it was 0. Yeah. So here I say, okay, c3, this is 1. Negative 1/4 plus c3 is equal to 0. So c3 is just 1/4. And I'm done. I have my position vector. So I have 10 d cubed over 3 plus d plus 0. So I'm not going to include that. My constant was 0 there. Here I have d minus sine of t plus 1. Because my C2, my other constant was 1. And lastly, I have negative 1/4 cosine of 2t plus C3. So plus 1/4. I could even factor it out, but it doesn't matter. I would say 1/4 times 1 minus cosine 2t or something like that. But yeah, I don't need to. That's it. Okay, let me type it in, see if it works. I have 10 t, oh, 10t over 3, I think. Yeah, and then t cubed. T cubed. Okay. Oh, I forgot to add the pluses. Um, yeah, so plus t, and then we have t minus sine t. I think we had 1 there, right? Yeah. Then negative 1/4. I think this was a cosine 2t. And then here I just add 1/4. Okay. Is that it? T minus negative 1/4 cosine 2t. Okay, let's see if my computation is right. Okay, I got it. Okay. For the other, yeah, I'm just gonna do the other ones in the next one because I don't want the video to be too long. I hope you guys learned something. I hope you enjoyed walking through velocity, speed, and acceleration of vectors. Honestly, without the pattern and without the redundancy, actually analyzing something like this in real life would be fascinating because you're able to identify not even a particle, I don't know, a plane. Um, yeah, through these vectors, velocity, speed, acceleration. I honestly think there's something cool and creative you can do with these calculus topics. So if you guys do something, well, I hope you share it to me because I'm also interested. But yeah, that's it for this video. I hope you guys enjoyed, and I'll see you all in the next one.